Welcome, fellow travelers of the cosmos, to an odyssey into the heart of some of the most enigmatic objects in the universe, black holes. Now, when most people think of black holes, they picture a cosmic vacuum cleaner relentlessly sucking up everything in sight. While that's not entirely inaccurate, it's a rather simplistic view of these celestial behemoths. You see, black holes are not just cosmic sinkholes, they're more like cosmic engines, playing a pivotal role in the evolution of galaxies. They sculpt galaxies, trigger star formation, and even influence the very fabric of space-time itself. We're about to embark on a journey to explore 22 distinct types of black holes, each with its own unique properties and cosmic influence. From the stellar mass black holes born from the death throes of massive stars, to the supermassive giants lurking at the centers of galaxies, we'll unravel their mysteries. We'll delve into the equations that define them, dissect the variables that govern their behavior, and explore their intricate dance with the galaxies they inhabit. Get ready for mind-bending concepts, stunning visuals, and a cosmic adventure that will take us to the very edge of our understanding. Buckle up, space fans, because things are about to get seriously black holy. Our first stop on this cosmic journey takes us to the remnants of massive stars, stellar black holes. These are born when stars, significantly more massive than our own sun, exhaust their nuclear fuel and can no longer support themselves against the relentless inward pull of gravity. Imagine a star, say 10 times the mass of our sun, collapsing under its own weight. The core implodes, crunching down to a point of infinite density, a singularity, and a black hole is born. Now, surrounding this singularity is a boundary we call the event horizon. This isn't a physical barrier you could bump into, but rather a point of no return. Cross the event horizon and you're not coming back. Not even light, the fastest thing in the universe, can escape its gravitational clutches. A key equation we use to understand these stellar corpses is the Schwarzschild radius, represented as Rs equals 2gm over c squared. This equation tells us how compressed an object needs to be to become a black hole. G is the gravitational constant, m is the mass of the object, and c is the speed of light. Now, if stellar black holes are the neighborhood bullies of the cosmos, then supermassive black holes are the galactic emperors. These behemoths, millions to billions of times the mass of our sun, reside at the centers of most, if not all, massive galaxies. Imagine the combined mass of millions, even billions of stars, crushed into a region smaller than our solar system. That's the scale of a supermassive black hole. They're the ultimate cosmic heavyweights, influencing the dynamics of entire galaxies. One way we study these galactic monsters is through their feeding habits. As gas and dust spiral towards a supermassive black hole, they form a swirling disk of superheated matter called an accretion disk. This process releases tremendous amounts of energy, often outshining the combined light of all the stars in the galaxy. We can describe the energy output of these accretion disks using the equation L equals EMC squared, where L is the luminosity, ETA is the efficiency of conversion of mass to energy, m is the rate of mass falling into the black hole, and c, again, is the speed of light. This equation highlights how even a small amount of mass, consumed by a supermassive black hole, can release staggering amounts of energy. We've discussed the stellar lightweights and the supermassive heavyweights of the black hole world. But the universe loves to remind us about the vast spectrum in between. That's where we find the cosmic middleweights, the intermediate mass black holes. These aren't your everyday black holes. They're bigger than stellar black holes, clocking in at hundreds to thousands of times the mass of our sun. But they're dwarfed by the supermassive behemoths that sit at the heart of galaxies. Their equation, while sharing similarities with their smaller counterparts, reflects this unique middle ground. It's a dance of gravity, mass, and the very fabric of space-time, but on a scale that makes them elusive and fascinating. These black holes are thought to be the missing link in black hole evolution, the stepping stone between their smaller siblings and the galactic giants. They could hold the key to understanding how supermassive black holes form and evolve over cosmic timescales. Now let's take a journey back in time to the very beginning, to the era of the Big Bang. Imagine a universe so young, so hot, so dense that even the laws of physics as we know them were still being written. In this chaotic cauldron, some theorists believe a new breed of black holes were born, primordial black holes. Unlike their stellar counterparts, these ancient objects didn't form from collapsing stars. Instead, they're thought to have emerged directly from the unimaginably dense energy fluctuations of the early universe. The equations describing these primordial black holes take us to the edge of known physics, grappling with concepts like quantum gravity and the very nature of space and time in the universe's infancy. They're like cosmic fossils, remnants of an era long gone, and their existence, if confirmed, could rewrite our understanding of the universe's earliest moments and the distribution of matter within it. We've scaled the heights of supermassive black holes and plumbed the depths of primordial mysteries. Now let's shrink down to the subatomic realm, a world governed by the strange and counterintuitive laws of quantum mechanics. Here, some theories propose the existence of micro-black holes, tiny singularities smaller than even an atom. These aren't your average black holes, gobbling up everything in sight. Their minuscule size means their gravitational pull is incredibly weak, far weaker than the fundamental forces that hold atoms together. Their equations, deeply rooted in the world of quantum mechanics, paint a picture of black holes that blink in and out of existence, popping in and out of the fabric of space-time like subatomic fireflies. While still theoretical, the existence of micro-black holes could have profound implications for our understanding of the universe, potentially offering a window into the unification of gravity and quantum mechanics, the holy grail of modern physics. Friends, we've journeyed through the cosmos, exploring the enigmatic realm of black holes. Prepare yourselves, for today, we delve into the realm of Kerr black holes, cosmic dancers perpetually caught in a dizzying pirouette. Unlike their more static cousins, Kerr black holes spin. As a Kerr black hole spins, it drags the very fabric of space-time along with it, creating powerful jets of radiation, shaping the evolution of entire galaxies. So, we've learned about Kerr black holes, those spinning giants. Now let's talk about a simpler kind, Schwarzschild black holes. If Kerr black holes are like spinning tops, Schwarzschild black holes are like still, heavy rocks. Their gravity is super strong, and they control everything around them. Back in 1915, right after Einstein shared his big idea about gravity, a scientist named Karl Schwarzschild made a huge discovery. He figured out how gravity works around a perfectly round, non-spinning star. This discovery led to the idea of Schwarzschild black holes. Picture this, a big empty space with just one giant star. The star runs out of energy and starts to shrink. It gets smaller and smaller and heavier and heavier. Eventually it gets so heavy that nothing, not even light, can escape its gravity. That, my friends, is a Schwarzschild black hole. These black holes are simple. They only have two main features, how heavy they are, and they don't spin at all. They might seem simple, but they're super important in space. Their gravity moves stars around in galaxies, and if anything gets too close, the black hole eats it up. GAP2S, they're like giant space vacuum cleaners cleaning up the universe. We've journeyed deep into the heart of darkness, exploring the realms of spinning Kerr black holes and the stoic gravity wells of Schwarzschild black holes. Now prepare yourselves for Reissner-Nordström black holes, where gravity and electricity engage in a cosmic dance. Most black holes form from collapsed stars which are electrically neutral. But what if a black hole could acquire a significant electric charge? That's where the story of Reissner-Nordström black holes begins. They challenge our understanding, possessing both gravity and electric fields. Imagine a black hole that could repel matter with the same ferocity that it attracts it. Talk about a cosmic tug of war. These black holes possess two event horizons, an inner and an outer horizon. It's like a cosmic fortress with a double-layered moat. We're just scratching the surface. Friends, we've talked about black holes that spin, the Kerr black holes, right? And we've discussed those with charge, like the Reissner-Nordström kind. But hold on to your cosmic hats, because now we're diving into the Kerr-Newman black hole. a cosmic beast that combines both these mind-blowing properties. Imagine a black hole, already a region of extreme gravity. Now add to it the dizzying spin of a cosmic ballerina, and as if that wasn't enough, throw in a massive electric charge. That, my friends, is a Kerr-Newman black hole. These aren't just theoretical curiosities, they represent a more realistic model of what we might encounter in the universe. The equations describing these behemoths are a bit more complex, naturally. They involve not just mass and spin but also charge, adding another layer to the already mind-bending mathematics. But fear not, we won't get bogged down in the equations themselves, though I encourage you to explore them further. Instead, let's talk about their impact on galaxies. A Kerr-Newman black hole's charge could influence the movement of charged particles in its accretion disk, leading to powerful jets of energy that could stretch for thousands of light years, shaping the evolution of their host galaxies. Wormholes. The very word evokes images of interstellar shortcuts and journeys through time. Could black holes be the cosmic tunnels we've dreamt of? Well, the equations of Einstein's general relativity do allow for the possibility of wormholes, often depicted as bridges connecting different points in space-time. Now, these theoretical tunnels are often visualized as being connected by black holes, or, more specifically, a black hole acting as an entrance and a hypothetical white hole as an exit. White holes, if they exist, would be the opposite of black holes, spewing out matter and energy. But here's the cosmic catch: while mathematically possible, wormholes are incredibly unstable. The immense gravitational forces at play would likely cause a wormhole to collapse faster than you can say quantum entanglement. And even if we could stabilize one, the amount of exotic matter with negative mass energy density required would be astronomical. While the idea of hopping through a wormhole to a distant galaxy is tantalizing, the reality is that wormhole black holes remain firmly in the realm of science fiction, for now. But hey, the universe is full of surprises, and our understanding of these cosmic enigmas is constantly evolving. So far, we've been talking about black holes as having a singularity at their core, a point of infinite density where the known laws of physics break down. But what if I told you some physicists believe black holes might not have singularities at all? Instead, they propose an intriguing alternative: fuzzballs. The fuzzball concept arises from string theory, which suggests that the universe's fundamental building blocks aren't point-like particles but rather tiny, vibrating strings of energy. In this framework, black holes are envisioned as giant, tangled balls of strings, hence the name fuzzballs. Now, unlike the point-like singularity, a fuzzball has a definite surface and volume. It's still incredibly dense, mind you, but not infinitely so. This eliminates the need for a singularity, which has always been a bit of a headache for physicists. The implications of black holes being fuzzballs are profound. For one, it could solve the information paradox, which questions what happens to information that falls into a black hole. In a fuzzball scenario, information wouldn't be lost, but rather encoded on the surface of the fuzzball itself. Now, whether fuzzballs truly exist is still up for debate, but it's a fascinating alternative view of these cosmic enigmas. We've journeyed deep into the cosmic wilderness, exploring black holes of all shapes and sizes. But what if I told you some of these enigmatic objects might not be black holes at all? We're talking about gravastars, hypothetical objects that challenge our understanding of gravity. Imagine a star on the verge of collapse, but instead of imploding into a singularity, it's held up by something extraordinary. This something is a shell of exotic matter, a state of matter so extreme it makes neutron stars look like fluffy clouds. This shell, my friends, is what we believe could be holding back the crushing force of gravity. Now, you might be wondering, how can we even begin to describe such a bizarre object mathematically? Well, it involves diving deep into Einstein's theory of general relativity. We're talking about equations that warp and bend the fabric of space-time itself. Equations that make your high school algebra look like child's play. But here's the kicker: the existence of gravastars is still purely theoretical. Observing them directly is like trying to find a firefly in a supernova explosion. But that's the beauty of astrophysics. Even in the face of such cosmic enigmas, we never stop searching, we never stop questioning, and we never stop exploring the universe's greatest mysteries. We've talked about black holes born from the remnants of collapsed stars, but what if I told you there might be black holes lurking out there made of something entirely different? Something invisible, something mysterious, something we call dark matter. Dark matter, as we know, makes up a significant chunk of the universe's mass, yet it interacts so weakly with light that it's practically invisible to us. Now imagine this elusive substance collapsing under its own gravity. Could it be that dark matter forms black holes distinct from their stellar counterparts? The equations governing dark matter's behavior are complex, and we're still trying to pin down its exact nature. But if dark matter black holes do exist, they could hold the key to unlocking some of the universe's most closely guarded secrets. They could explain the unusual rotation curves of galaxies, or even the very structure of the cosmic web itself. Think about it, black holes we can barely detect, influencing the evolution of galaxies on a grand scale. It's a tantalizing thought, pushing the boundaries of our understanding and reminding us that the universe always has more surprises in store. We've encountered black holes that devour everything in their path, but what about objects caught in a cosmic balancing act, teetering on the edge of becoming black holes but not quite crossing that event horizon? Welcome to the realm of quasi-black holes. These intriguing objects are thought to be incredibly dense, even denser than neutron stars, but not quite dense enough to form a true singularity. They're like cosmic daredevils, pushing the limits of gravity without taking the final plunge. Now you might be wondering, what keeps these quasi-black holes from collapsing completely? Well, some theories suggest that exotic quantum effects, the same forces that govern the behavior of particles at the subatomic level, might be at play. These effects could create an outward pressure, counteracting the relentless inward pull of gravity. Quasi-black holes represent a fascinating gray area in our understanding of gravitational collapse. Welcome back, fellow explorers of the cosmos. Today we're diving into the world of magnetically charged black holes. These fields play a crucial role in how black holes devour matter. They launch jets of energy and matter, stretching thousands of light years. These jets influence star formation and sculpt galaxies. It's a cosmic ballet of gravity and magnetism. We've talked about black holes that are millions, even billions of times the mass of our sun, but what about black holes so small they make an atom look like a giant? These tiny titans, Planck-scale black holes, emerged from the Big Bang's chaos. Imagine a hot, dense soup of energy and particles where quantum fluctuations spawned these miniature black holes. They could unlock the universe's deepest secrets. Black holes, as we've explored, are cosmic enigmas, pushing the boundaries of our understanding of physics. But what happens when you throw the bizarre world of quantum mechanics into the mix? Hold on tight, because we're about to enter the perplexing realm of firewall black holes. Now remember the event horizon, that point of no return beyond which even light can't escape? Well, according to some theories, the event horizon might not be as smooth and empty as we once thought. Instead, it could be a seething inferno of high-energy particles, a firewall, if you will. This firewall paradox arises from the clash between general relativity, which predicts a smooth event horizon, and quantum mechanics, which suggests that information cannot be destroyed, even within a black hole. If information is preserved, how and where is it stored as it falls into a black hole? The firewall hypothesis proposes that information is encoded and re-emitted at the event horizon, creating a blazing wall of energy. Now this idea is highly debated and we don't have definitive answers yet, but the implications are mind-blowing. If firewalls exist, they could revolutionize our understanding of black holes, quantum mechanics, and the very nature of information itself. We've talked about black holes, those cosmic abysses so dense that not even light can escape their gravitational clutches. But have you ever pondered their theoretical counterparts, white holes? Imagine, if you will, a region of space-time where nothing can enter, but matter and energy are constantly being ejected. This is the essence of a white hole, a cosmic fountain, spewing forth the universe's building blocks. Now picture this, a white hole inextricably linked to a black hole, forming a mind-boggling cosmic conduit. This is the concept of a white hole-black hole pair. a theoretical phenomenon that truly stretches the limits of our understanding. Some physicists propose that these pairs could be connected through wormholes, those hypothetical tunnels through the fabric of space-time. Matter falling into the black hole might then be transported through this cosmic shortcut and ejected from the white hole, potentially in a distant part of the universe or even a different universe altogether. While purely theoretical at this point, the idea of white hole-black hole pairs is captivating. It underscores the sheer strangeness of the cosmos and the tantalizing mysteries that continue to beckon us deeper into the unknown. Black holes, as we've explored, are some of the most extreme objects in the universe, but the cosmos, as always, has a knack for pushing boundaries. Beyond the familiar event horizon and singularity, theoretical physics predicts a whole menagerie of bizarre entities known as exotic compact objects. These hypothetical objects share some characteristics with black holes, like immense density and strong gravitational pull, but they differ in crucial ways. Take for instance the Gravistar. This theoretical object is thought to be a shell of ultra-dense matter supported by a kind of exotic pressure, potentially arising from quantum gravitational effects. Then there are fuzzballs, a concept emerging from string theory. Imagine, if you will, a black hole, not as a point-like singularity, but a fuzzy ball of strings, the fundamental building blocks of the universe according to string theory. These fuzzballs, unlike black holes, are thought to have no singularity at their core and might even possess a kind of surface. While observational evidence for exotic compact objects remains elusive, their theoretical possibility challenges our assumptions about the nature of gravity, space-time, and the very fabric of reality. We often think of black holes as colossal objects, millions or even billions of times the mass of our sun. But what if I told you that scientists are now creating black holes right here on Earth? Now hold on, I'm not talking about city-swallowing cosmic monsters. These are Bose-Einstein condensate, BEC black holes, microscopic entities formed within laboratories. A BEC is a state of matter where separate atoms, cooled to near absolute zero, begin to behave like a single quantum mechanical entity. They essentially become one giant atom, exhibiting strange and fascinating properties. Now imagine creating a sonic analog of a black hole within such a BC, a region from which sound waves, instead of light, cannot escape. Scientists achieve this by manipulating the flow of the condensate, essentially creating a region where the flow speed exceeds the speed of sound within the condensate itself. This sonic event horizon mimics the event horizon of a black hole, trapping sound waves and allowing researchers to study the behavior of quantum phenomena in extreme conditions. While BEC black holes are a far cry from their astrophysical counterparts, they offer a unique window into the interplay of gravity, quantum mechanics, and the fundamental laws governing our universe. We've explored a vast menagerie of black holes, haven't we? From the stellar to the supermassive, each with its own cosmic signature. But what if I told you our universe might be stranger than we ever imagined? What if there were more than just the three spatial dimensions we experience every day? That's right, some theories propose the existence of extra dimensions, curled up and hidden from our perception. And within these higher dimensions we might find, you guessed it, black holes. But these wouldn't be your average cosmic vacuum cleaners. These hypothetical, higher-dimensional black holes could have properties unlike anything we've discussed. Their event horizons, their shadows, even their very structure, all could be profoundly different. Imagine a black hole not as a sphere but as a multidimensional object with an event horizon that defies our conventional understanding of geometry. While currently in the realm of theoretical physics, the possibility of higher-dimensional black holes reminds us that the universe loves to surprise us. It challenges us to expand our minds, to venture beyond the familiar, and to embrace the truly mind-boggling possibilities that the cosmos holds. Buckle up, cosmic explorers, because we're about to dive into the realm of science fiction, or is it? Warp black holes, as the name suggests, are theoretical objects that would allow us to manipulate the very fabric of space-time, to warp it, to bend it, and perhaps even to travel through it in ways we once thought impossible. Imagine a black hole, but instead of just sucking things in, it also has an exit point, a white hole. spewing out matter and energy elsewhere in the universe, or even in a different universe altogether. This cosmic shortcut, this tunnel through the cosmos, is what we call a wormhole. Now, creating a warp black hole is no mean feat. It would require harnessing energy on a scale that dwarfs anything we can currently fathom. We're talking about manipulating the fundamental forces of the universe, bending space-time to our will. But hey, if there's one thing we've learned from exploring the cosmos, it's that the universe is full of surprises. While warp black holes remain firmly in the realm of speculation, the very concept ignites our imagination, urging us to push the boundaries of what we think is possible. From the stellar nurseries where they're born to the galactic centers they sculpt, black holes have revealed themselves to be not just cosmic oddities, but fundamental players in the grand cosmic drama. We've journeyed through a cosmic zoo of black holes, from the relatively mundane to the truly mind-bending. We've seen how these gravitational behemoths, once thought to be mere mathematical curiosities, hold sway over the evolution of galaxies, influencing the birth of stars, the dance of gas clouds, and even the fate of the universe itself. And we've done it all through the lens of mathematics, the language of the cosmos, the key to unlocking the secrets of the universe. But our journey doesn't end here. The universe is vast, its mysteries deeper than we can even imagine. So keep looking up, keep asking questions, and never stop exploring the universe and all its wonders, because the more we learn, the more we realize how much more there is to discover.